All right, guys, so what we're doing today is starting chapter 5. We're starting chapter 5 today. Rational exponents and rational functions. So chapter 5 is the last chapter we're covering this year. So this is it. But what we're doing with this here is our radicals, square roots, cubed roots. Now the first thing we're looking at is this here, square root of 64 and the cubed root of 64. Which one is bigger?
Cube root?
So let's see. So what would the square root of 64 be? 8, because what times itself is 64? Now, the cubed root of 64, we want to know what multiplied by itself 3 times is 64. Because the square root of 64 is indeed 8. The cubed root of 64 is 4. The square root is bigger. Because when we increase the index, we're saying that that number is being multiplied by itself more times, so it's going to be getting smaller. Now, if we took, say, the 6th root of 64, we get 2. And that's about the last nice root we can take with 64. But as the index increases, the index is our number right here. It's the root of our radical. We get this here. Now the first set of stuff that we're going to do in these first few problems is more getting us used to switching between a rational exponent and radicals. And we've had this before, that the nth root of a is equal to a to the 1 over n. Now we can take this a little bit farther, because this is true. But it also works out that the nth root of a to the x, well, the n still goes on bottom. But our x, our exponent, actually goes on top. We can say the nth root of a to the x is equal to a to the x over n. And we can do this here. Now, switching it between different versions does work, because we could set it up so that we have the nth root of a to the x, or have the nth root of that extra parenthesis, or we can have the nth root of a to the x. We can have it in either form. It's just going to be dependent on what's going to be more useful in simplifying. But the key thing is that the nth root of a to the x is equal to a to the x over n. We can switch from one to the other. Now this is kind of useful, and it's kind of nice to know, because this does explain some things to us. Because one of them is the square root of a squared. We've had this before. We've looked at things like this before, especially in Algebra 1. And we normally went and crossed them out and just said that the square root of a squared is a. Square root and squares cancel. Now, if we use this property that we have here, the index, even though we didn't write it, is 2, because the square root's index is 2. Well, that index 2 goes on bottom, and our exponent of 2 goes on top. So the square root of a squared is the same as a to the 2 over 2. Well, 2 divided by 2 is, so it's just the same as a to the first, or just a. This is why a square root and square will cancel. I mean, we could say that we have the 873rd root of a to the 873. All we're saying is that we have a to the 873 over 873, which is just a. They simplify out. And this can be helpful, especially when simplifying radicals. But this explains why when the index of the radical and the exponent are the same, they simplify out. This is why this works. Questions on this here? We good with this so far? We've kind of seen how this works. This is kind of nice. Now, the next bit of stuff that we're going to do, we'll do some simplifying some other things, but really what we're going to be looking at is how we can use this property, this definition of rational exponents. And again, I need to get rid of that slide. I don't like it, because it really doesn't tell us much. So this is what we're going to look at first, the square root of 5 to the third. And for these next 3 or 4, we're going to rewrite it from radical to our rational exponent. We're going to rewrite it as a rational exponent. Now the square root of 5, if we're going to rewrite it as a rational exponent, it's going to be 5 to an exponent. And that exponent is going to be fractional. Now the number on top is the exponent attached to 5. Well, that would be 1. Since it's not written, it's understood to be 1. We do have the 3 outside, but it's going to come into play in a minute. Now what's our index? 2. Because whenever it's not written, it's understood to be 2. So the square root of 5 is the same as 5 to the 1/2. We good with that there? Powers of powers. Multiply. So 5 to the 1/2 to the third, or 1/2 and 3 multiply together to give us 1.5 or 3/2. And that's as far as we're going to take this here, because we could convert it to a decimal, and if it did ask us to evaluate this around to 3 decimal places, we would do that. And I could take the calculator. 5 to the 3/2, which is 11.1803399, and it continues on. And what did we start with? We started with the square root of 5 to the third, which incidentally is the exact same thing. We did have the same thing. Because again, this first part is not so much about solving or evaluating. I want us to get a little bit familiar with switching from one form to the other, because it is a little weird, it's a little strange that we can do this, but that's what we have. Let's look at the next one, the 4th root of 4 squared. Now if we want to rewrite the 4th root of 4 as a rational exponent, we would have 4 to the what? We'd have 4 to the 1/4. The 1 comes from the exponent attached immediately to the 4. We're not looking so much at the 2, but with the 4. Now, if it had been 4 squared, the top would be 2. Does that make sense between the two? Now, the 4 comes with our index of 4. So we have 4 to the 1/4 squared. Powers of powers, multiply. Now, what is 1/4 times 2? Which is? Yeah, because 2 times 1/4 is indeed 2/4, but 2 over 4 reduces to 1/2. So we have 4 to the 1/2. And again, we can make sure that these are the same. 4 to the 1/2 gives us this ugly decimal, yes? No. Gives us 2. No. 4 square is indeed 2. Now this might be interesting because we can look back at it and see why this is the case. Because this is 2. Well, 4 to the 1/2. If we rewrote this as a radical, the 4 would be inside to the first power. And well, the index would be 2. So we're looking at the square root of 4, which is, incidentally, 2. So it did work out nicely. Because not every radical will give us an irrational number, but a lot of them do. Because that's why this reduced to 4, because really our 4 to the 1/2 is the square root of 4. Questions on this here? So some of these do reduce nicely, some of them don't. Let's look at C. The cubed root of 9 squared. Well, the cubed root of 9.
I thought you were itching.
No, because I'm going to turn around and start digging.
We can rewrite as 9 to the, what, 1/3. Now our 9 to the 1/3 squared would be 9 to the 2/3. Powers of powers multiply. 9 to the 2/3 is this here.
No, it's not. That's not 6. Sorry, I'm confused. Ow!
Cube root of 9 square is this here. Because our cube root of 9, there's not a number multiplied by itself. 3 times that'll give us 9, and squaring it's not going to make a difference. Because the only reason the other one did, it was working off the fact that 4, if we simplify 4, 4 is the same as 2 squared. So we could have said it's 2 squared to the 1/4, which would simplify. But questions on this here? We feel kind of comfortable going from these radical to rational exponents. Yes? Well, we're going to skip ahead to 8 to the 2/3. Now we're going to go from the rational exponents to radicals. And we'll do it in parts, kind of break it down to what we have. Now our 8 to the 2/3, one of the ways we can look at this is 8 to the 1/3 squared. So we're kind of going backwards from what we did previous. Because we would simplify the radical first and then apply the power to it. So we're going to break it back apart first, because our 2/3 is the same as 1/3 to the second power, our 1/3 times 2. Now 8 to the 1/3 is the same as, we'd have a radical in 8. The exponent attached to the 8 would be 1. And the number index would be 3. Because the number on top goes with our number, the number on bottom is the index going in that V for the radical. And that's it, because we have it rewritten. Now it'd be nice if we could take the cubed root of 8. Is there a number multiplied by itself 3 times that gives us 8? And there actually is 2. Mm-hmm. And 2 squared is? Oh. Mm-hmm. Because we could say that this is the same as the cubed root of 8 squared. Well, the cubed root of 8 squared is 64. And well, the cubed root of 64 is 4. There's different ways we can do it with applying power, because the power can be inside or out. We do have to be a little careful when the exponent is, our root is even, but when the root is odd, it works kind of nicely. Let's look at 6 to the 5/2. Well, we could say this is the same as 6 to the 1/2 to the 5th. Well, our 6 to the 1/2 is the same as the, so we do our radical and put the 6 inside. Since our denominator of the fraction is 2, our index is 2, so we could write it. We don't have to, because it's understood to be a square root. And we actually have this here. This is as far as it goes. It just worked out nicely that the one before did simplify further. Questions on this here on rewriting these? We'll do one more, but not too bad so far switching from one to the other. because sometimes it's easier to evaluate it in one form or the other. Well, I'm going to skip ahead to these two. Evaluate without a calculator. So it is possible to evaluate these without using a calculator. 4 to the 3 halves. Again, I would do exactly what we did on the previous one. First thing I would do is split up 3 halves, because doing 4 to the 3 halves without a calculator might be a little challenging. But if I split it up this here, 4 to the 1/2 cubed, well, 1/2 is the same as what? The square root of 4. Now we know what the square root of 4 is. Square root of 4 is what? 2. So now we're saying we're taking 2 to the cube, the third power, and 2 to the third power is 8. And that's it. And again, there's more than one way to do this. We could take it the other way, because our nth root of a to the x is equal to a to the x over n. So the 2 would still be here, but our 4 would be to the third. And this is going off again. Our a to the x over n is equal to the nth root of a to the x. Now our 4 to the third is 64. And the square root of 64 is still 8. Questions on this here? Or the easiest way is if we used a calculator. Questions on A? Now, 32. We could take this as 32 to the 1/5 to the 4th. We can break that exponent up, because our 1/5 to the 4th is the same as 4/5. Our powers are powers multiply. We feel comfortable with this here? Yes? Now the question is, what times itself 5 times is 32? If you were to take a guess, what number do we think would be? There is. So,
6.5.
and it's going to be a nice number. What times itself 5 times is 32? So what number do we think? So 7. So 7 times 7 is 49. So we'd multiply it again. 3 carry the 6 would be 343. Because, yeah. So we can stop there. What times itself? 32. 2. Let's try 2. 2 times 2, 2 squared is 4. 4 times 2 is 8. So 8, or 2 cubed is 8. Times 2 is, so 2 to the 4th is 16. So 32 to the 1/5 is 2. We're saying 2 times itself 5 times is 32. And that leaves us with 2 to the 4th. And 2 to the 4th power is 16. That's it. I mean, we could try the other way that we did, especially with the previous one, in that we're taking the 5th root of 32 to the 4th power. I don't think this is advisable, because we're going to have to multiply 32 by itself 4 times and then take the 5th root of whatever that number is. Because at that point, we'd really need a calculator, because 32 to the 4th is 1,048,576, and then trying to find a number that multiplies by itself 5 times, that gives us that. It might be easier to go the other way. Do we kind of see that? So sometimes, like the previous one, it didn't make a real big difference which way we did. Here, we ended up getting a bigger number. We still get to the same answer. 5th root of 10,48576. is still 16, but sometimes one way is easier than the other. Questions on this here. 625 to the 3/4. Well,
Without a calculator?
now, this one here, I would not rewrite this as the 4th root of 625 to the 3rd, because that means we'd have to multiply 625 by itself 3 times. But our 1/4 is telling us that we're taking the 4th root of 625 and then putting it to the 3rd power. So the question is, what times itself 4 times is 625? 4 times. So if we did 5, 5 times 5 is 25. If we multiply it again to get cubed, we'd have 5, carry the 2, which would be 125. And if we do it one more time, 5, 2, 10, there's 1, 5 times 1 is 5, plus 1 is 6. So the 4th root of 625 is 5. And 5 to the 3rd power is, and that's it. We're going to do one more. 49 to the 3/2. Well, we could say that this is the same as 49 to the 1/2 to the 3rd. Well, the 1/2 is the same as the square root. So we're wanting to take the square root of 49, which is 7. Now 7 to the 3rd is, and we actually did that earlier this hour. Questions on this here? Now, if you notice something on these last 4, if the exponent's less than 1, is our final number bigger or smaller than what we started with? Because here, 625, 3/4, we ended up with 125, yes? If you look at the previous one, 32 to the 4/5, we ended up with 16. We went from 32 to, here, the exponent was bigger than 1, so we went from 4 to 8. Here, we went from 49 to, so if the exponent's bigger than 1, we're going to increase. If it's less, between 0 and 1, it's going to decrease. Questions on this here? We good with this here? Yes? We ready for the hard stuff? Okay. Nth root, real nth roots of A. When we're taking the nth root of A, so we're going to look at when n is an odd number, n is an odd integer. So we're looking at the cubed root, the 5th root, the 7th root, the 9th root, when n is odd. Now, guys, let's focus in here. If n is an odd number and the number inside is less than 0, so if this number was negative, say -8, we have one real root, and we would simplify and get that root. Now, if the integer, again, an odd integer in A, the number inside is 0, we have one real root. And if A is greater than 1, A is a real number, so any real number, we could say the cubed root of 16. We have exactly one real root. Confusing? If the index is odd, we either have one real root, or one real root. I mean, if we have an odd root, we're only going to have one answer. Doesn't matter what it is. Now let's look at even. If we take the even root of something, so the 4th root, 6th root, 2nd, so our square root, 4th root, 6th root, 8th root, anything that's an even root, we have one of 3 options. If the number is positive, greater than 0, we have two real roots, we have to add the plus or minus to it because it could be positive or negative. And this is when we're adding it to it, not the ones we did before. We're taking the even root, guys. We're taking the even root of it. Okay? Now, if a is 0, we have one real root because the even root of 0 is just 0. Nothing really to it. And the last one is a is less than 0. If a is a negative number, so negative 16, we have no real roots because this would be plus or minus 2i. I is not a real number, so we do not have real roots if we have an even root of a negative. We just say no real roots. If we're asking to find the solution of the fourth root of negative 16, it would be positive or negative 2i. But here we're wanting to find the real root. So if it's asking for the real root, we have no real roots. If a is negative and our n is even. Okay. Let's look at the first one here. We want to find the indicated real nth root of a. And for these here, all we're doing is taking the nth root of a. Now for our first one here, the n is 3. A is negative 216. So when we look at this here, our n is 3. N is odd. Our root is odd. So we have one of three options. We either have one real root, or one real root. At this point here, we can go 3. Third root of negative 216 is negative 6. So our answer for this here is negative 6. And that works just fine because our negative times a negative is a positive, times one more negative gives us back to a negative. And our 6 times 6 times 6 is indeed negative. Is 216. Questions on A? B. N is 4, so we'll put 4 in as our index. A is 81. Now, since the index for the second one is even, we either have no real roots, one real root, or 2. None if it's less than 0, 1 if it's equal to 0, or 2 if it's greater than 0. And here, 81 is greater than 0, so we will have 2 real roots. We have to put the plus or minus. Now we can say the fourth root of 81 is 3. So the fourth root of 81 is plus or minus 3. Now if they'd have just given us the fourth root of 81 to start with, we would say 3. But here, since we're applying the fourth root to it, we do plus or minus. Questions on these two here? N is 4, A is 16, so we're wanting the fourth root of 16. Again, just like the previous one, our index is even. And since the number inside is positive, we have two solutions, plus or minus. Now our fourth root of 16 is questions on these first three that we've done. Our next one, our index is 2, so we don't actually have to write it because it's understood. We can write it, there's nothing wrong with that. But we can leave it as the square root of negative 49. Now, since the index is even, we either have no real roots, one real root, or 2. Because the index is even, and the number inside is negative, yes? So this is plus or minus 7i. But because the number inside is negative, we have no real nth roots. We have no real nth roots. There are roots for it, but they're imaginary. And here, we're not asking for the imaginary roots. We're just asking for the real root. We want to find the indicated real root. So here, There are no real roots, because we cannot take the even root of a negative number. Questions on this here? N is 3 and A is negative 125. So here we're wanting to take the cubed root of negative 125. You need to step out and collect yourself. So here, because it's an odd root, we will have one solution, one real solution, and it works out to be negative 5. Because we could have the calculator and it will tell us our solution. And the last one, our n is 5, and our number is 243. Now, since the root is odd, we will have one real root. And again, we can plug this into a calculator. And it works out the answer is 3. Questions on this here? And that is it for this here.